Welcome to the deep dive. Today we're diving deep into robust machine learning. It's a critical area, and we've got a ton of really interesting research to unpack. We'll be focusing on the vulnerabilities and defenses of ML systems, both in terms of security and reliability.
Yeah, this collection of research is fascinating because it really shows a shift, from just focusing on model accuracy to understanding the bigger picture of robustness. We're going beyond just the algorithms themselves.
Exactly. Really looking at the whole ML ecosystem. It's like recognizing that a model's performance is tied to how resilient it is against all kinds of threats. But before we get into the specifics, maybe let's quickly go over some basics like neural networks, the ML design cycle, and how these systems are deployed.
Right, those foundations are key because the type of vulnerability you encounter often depends on where it's deployed.
Yep.
Cloud-based systems, which are mostly used for training, are susceptible to things like data poisoning and IP theft. But then you have edge devices that are used for inference. They're more vulnerable to hardware faults and even something like environmental noise.
Okay, so let's get into specifics. The research goes deep into some pretty crazy security vulnerabilities, like adversarial attacks. These are like something out of a movie.
Yeah, they're pretty ingenious, actually. Attackers can add this almost invisible noise to the input data, and that tricks the model into misclassifying it. Like, imagine a stop sign for an autonomous vehicle, but it's slightly altered so the car sees it as a speed limit sign. Obviously, the consequences could be really bad.
Yeah, that's a scary thought. And these attacks can happen during both training and inference, right?
Exactly. Evasion attacks target the inference stage, when the model is already trained. They exploit those learned parameters to craft those bad inputs. Then you have poisoning attacks, which inject corrupted data during training. So basically, they're compromising the model from the ground up.
So you're saying there are attacks that hit the model after it's trained and attacks that corrupt the training itself. What a mess.
Yeah. It's a tricky landscape for sure. And there are even variations within those categories, like backdoor attacks. They exploit these dormant neurons inside the network. They only trigger misclassifications when they see very specific inputs. It's like a constant battle between attackers and
It
defenders.
reminds me of neural level Trojans. I think the research talked about those too. What exactly are they?
Oh, those are especially sneaky. It's like having these malicious extra neurons embedded in the network. They just sit there dormant until they're triggered by specific inputs, and then they cause problems. It's basically a time bomb within the model itself.
So now we're moving beyond just algorithms into hardware, right? The research talked about hardware-based attacks, like hardware Trojans. What are those all about?
So with hardware Trojans, you're talking about malicious components that are physically implanted in the hardware during manufacturing. They might be dormant, waiting for the right moment to activate, or they could be leaking information all the time, maybe even leading to IP theft. It's basically like having a spy embedded at the heart of the system.
And then there are side channel attacks, which seem even sneakier.
Yeah, side channel attacks are all about exploiting information leakage from the hardware, like power consumption or electromagnetic emissions. By analyzing those leakages, attackers can figure out how the model works or even steal sensitive data. It's pretty sophisticated stuff.
It sounds like to really secure an ML system, you need to address vulnerabilities in both the software and the hardware.
Absolutely. It's a multi-layered problem. And of course, we can't forget about IP theft, which can happen in a couple of main ways.
Oh, yeah. How do attackers go after a model's intellectual property?
Well, there's model stealing, where attackers try to make a copy of the target model by probing it with different inputs. And then there's data set stealing, where they try to recreate the original training data based on how the model behaves. Both of these can cause serious economic and competitive damage.
Okay, so we've got all these security threats to worry about. But the research also goes into the defenses that are being developed.
Right, and this is where things get really interesting. There's a whole range of defense mechanisms, each with its own strengths and weaknesses.
Let's start with defenses against those tricky adversarial attacks. What are some of the things people are working on?
One approach is called gradient masking. It's basically trying to hide the model's gradients from attackers, making it harder to craft those adversarial inputs.
That's like camouflaging the model's inner workings.
Yeah, exactly. Another powerful technique is adversarial training, where you actually train the model on adversarial examples. It's like giving the model a sparring partner to get it ready for the real fight. It learns to recognize and resist those attacks.
Makes sense. But I imagine attackers could always come up with new attacks that get around even these defenses. It feels like an arms race.
You're right, it's a constant back and forth. That's why things like input pre-processing are so important. Techniques like filtering or smoothing the input data, it's like adding an extra layer of protection.
So those are for defending against attacks that target the model's behavior. What about those neural level and hardware Trojans, the ones hiding inside the system.
For neural level Trojans, pruning techniques can help remove those dormant neurons, making it harder for them to hide.
So it's like cleaning up the neural network, getting rid of anything unnecessary that could be causing trouble.
That's a good way to put it. And for hardware Trojans, you can use formal methods like equivalence checking to make sure the hardware is actually doing what it's supposed to.
So that's using math to verify that there are no hidden surprises in the hardware. What about protecting a model's IP from those stealing attempts?
For data protection, encryption is crucial, especially when you're using third-party servers for training. Runtime monitoring can also help catch suspicious activities, and then there are obfuscation techniques that make it harder to reverse engineer the model.
All of this is really fascinating, but it makes me wonder, is it even possible to make an ML system completely secure with all these vulnerabilities?
It's a tough challenge, but the field is always evolving. The key is to use a multi-layered defense approach, combining different strategies to build a strong security posture. But security is just one part of robustness.
Right. There are also reliability threats, where you don't necessarily have a malicious attacker. These seem to come from problems in the hardware or software themselves.
Exactly. With reliability, we're dealing with vulnerabilities that come from hardware faults or weird things happening within the neural network itself.
So let's talk about those hardware faults. What kind of issues are we talking about here?
Well, we can break them down into three main types. First, there are transient faults. These are temporary errors, often caused by things like radiation or temperature changes. They can flip bits in memory or mess up logic circuits, which could lead to wrong classifications.
And then there are intermittent faults. Those sound like a real pain to figure out.
Yeah, intermittent faults are these recurring glitches that can happen because of things like variations in the manufacturing process or just the hardware getting old. They're tricky because they don't always happen consistently.
And lastly, there are permanent faults, which sound pretty much impossible to fix.
Yeah, permanent faults are basically irreversible damage, like stuck-at faults, where you need to replace the hardware. They can happen from things like cosmic radiation, static electricity, or even just a bunch of intermittent faults building up over time.
It makes you realize why I prefer working with software. Hardware seems so fragile. But with all these different faults, how do you even start to mitigate these hardware problems?
There are a few approaches. For transient faults, especially in memory systems, error detection and correction codes are commonly used. And then there are redundancy and voting mechanisms, where you use multiple copies of a component and compare their outputs to catch and correct errors.
So it's like having a backup system in case one part fails, a kind of safety net for hardware.
Exactly. And for intermittent faults, you can use techniques like age-aware workload management to spread the work evenly across different components so you don't wear out one area too quickly.
That's pretty clever. What about permanent faults? Do you always have to replace the whole chip?
Not always. Sometimes you can just ignore the affected bits or bytes, which is cheaper and less disruptive. And for ML systems specifically, there are techniques like fault-aware training or pruning that can help.
Fault-aware training? What's that about?
It involves training the DNN on data sets that simulate different kinds of hardware faults. This way, the model learns to be more resilient to those specific faults.
So you're basically exposing the model to potential hardware problems in advance to make it tougher. It's like giving it a crash course in dealing with unexpected hardware behavior.
Exactly. And pruning, in this context, means getting rid of connections and parameters that are linked to faulty hardware elements so they don't affect the model's output.
So it's like surgically removing the problematic parts of the network. It seems like there are a lot of different strategies for dealing with these hardware issues. But what about those neural network anomalies you mentioned earlier? What causes those and how do you address them?
Right, these anomalies aren't caused by hardware problems, but by limitations within the neural network itself. For example, things like fog or changes in lighting can really mess up computer vision systems.
Oh, like those examples we see where self-driving cars misclassify objects because of subtle changes in the environment. It's almost like the model is too sensitive to things it hasn't been trained on.
Exactly. And these anomalies can also happen because of variations in how data is collected, like changes in camera angle or brightness. Basically, these systems can struggle to generalize to new inputs, especially ones that are close to the decision boundaries.
So it's like the model is overfitting to the specific data it was trained on. It's not flexible enough to handle variations in the real world.
You got it. And to fix this, we can actually use some of the same techniques we talked about for adversarial attacks, like pre-processing filters and adversarial training.
So it's about making the model more robust to noise and variations in the input data. Are there any other techniques specifically for dealing with these neural network anomalies?
Yeah, we can also use synthetic datasets to help the model generalize better.
Synthetic data sets, what are those?
These are datasets that are artificially generated to cover a wider range of possible inputs, including things like variations and noise that you might not find in real-world data.
So it's like creating a virtual training ground to prepare the model for anything it might encounter in the real world.
Exactly. But creating synthetic datasets that are truly representative can be tough,
Mhm.
especially for complex real-world situations.
It sounds like building really robust ML systems requires a deep understanding of both the algorithms and the hardware they run on. It's a really multifaceted challenge.
Absolutely. And there's one more important aspect we haven't talked about yet: formal verification.
Ah, yes. This is where things get really interesting. We're talking about using math to actually guarantee that ML systems are working correctly. It seems like that would bring a whole new level of rigor to robustness.
You got it. Formal verification is a powerful tool, especially for things like safety-critical applications where even small mistakes can be disastrous.
So why is formal verification so important, especially for deep neural networks? What makes them so hard to verify using traditional methods?
Traditional testing, where you try out the model on a bunch of different inputs, just isn't enough for DNNs. They often have trouble generalizing to new inputs, and they're so complex that it's almost impossible to test every possible scenario.
So formal verification lets us mathematically prove that the system will work correctly under any conditions.
That sounds amazing, but also incredibly difficult.
In theory, yes. But formal verification of DNNs is still a pretty new area, and there are different approaches, each with its own pros and cons. Okay, let's talk about those different approaches. The research mentions four main categories: SAT-SMT solving, linear programming, interactive theorem proving, and incomplete verification.
Right. Let's start with SAT-SMT solving. This involves representing the neural network and its properties as logical formulas, and then using solvers to check if those properties hold true.
So you're basically turning the neural network into a math puzzle and letting computers solve it to verify that it's working right.
That's a good way to think about it. SAT solvers work with propositional logic, which makes them good for verifying binarized neural networks. SMT solvers, on the other hand, can handle more complex theories, so they can verify DNNs with real-valued parameters.
That's pretty impressive, but I'm guessing there are some limitations, especially with real-world DNNs, which can be super complex.
You're right. Scalability is a big challenge for SAT-SMT-based verification. Right now, these techniques can handle relatively small networks, but they struggle with larger, more complicated ones. There's a lot of research going on to optimize these solvers and make them more scalable.
What about linear programming? How does that approach verification?
With linear programming, or LP, you define the network and its properties as a set of linear constraints, and then you have an objective function. LP solvers are used to find the best solution that satisfies those constraints.
So it's like finding the best outcome within a set of rules defined by the network.
Exactly. LP is often used to analyze how robust DNNs are against adversarial attacks. It can tell you the minimum amount of noise needed to cause a misclassification.
That's useful information. But I'm guessing there are limitations here too, especially since neural networks often use functions that aren't linear.
You're right. The main problem with LP is that it needs the constraints to be linear. But DNNs often use nonlinear activation functions, which are hard to represent accurately with LP. There are ways to use linear approximations, but that can lead to incomplete verification results.
Ah, so you're trading off accuracy for scalability. Are there any ways to improve the accuracy of LP-based verification without sacrificing too much scalability?
There are techniques like Big M encoding that try to improve accuracy, but scalability is still a challenge. Now, let's talk about interactive theorem proving. This approach is more hands-on and theoretical.
This one sounds like it involves a lot of human effort. Less about automated solvers and more about using human expertise.
That's right. Interactive theorem proving requires a deep understanding of how the DNN works, and it involves building mathematical proofs to verify its properties.
So it's like having a mathematician double-checking every step of the DNN's logic, making sure everything is correct.
Exactly. This approach can provide really strong guarantees, but it's very complex and time-consuming. You need experts in both formal verification and the specific DNN architecture.
It sounds like this method is better suited for proving fundamental theorems about DNNs, rather than analyzing specific implementations. It's more about proving core principles than dissecting particular models.
You're exactly right. Interactive theorem proving has been used to verify things like the perceptron convergence theorem, but using it for larger real-world DNNs is still limited.
Okay, and finally, there's incomplete verification. What's that all about, and how is it different from the other methods?
Incomplete verification, as the name suggests, doesn't give you complete guarantees. It often involves simplifying the DNN model, using techniques like abstraction or linear approximation to make it easier to verify.
So it's like creating a simplified version of the DNN to make it easier to analyze.
That's a good way to put it. This approach is often more scalable than complete verification methods, but it can lead to false positives.
False positives. That sounds worrying.
Yeah.
Wouldn't that give you a false sense of security?
Yeah, it means the verification might say that the DNN is safe when it's actually not. That's because the simplified model might not capture all the details of the real DNN's behavior. So you're trading off completeness for scalability.
So there's this trade-off between being able to handle large systems and getting completely accurate results. Are there ways to reduce the risk of false positives when using incomplete verification?
Researchers are working on that. One promising approach is to combine incomplete verification with complete verification methods, using the strengths of both. You get the scalability of incomplete methods and the accuracy of complete methods. It's about finding the right balance.
This exploration of formal verification has been really interesting. It seems like a field with huge potential, but there's still a lot of challenges.
Absolutely. Formally verifying complex, real-world DNNs is a really tough problem, and there's a lot more research to be done. It's a fascinating area for anyone who wants to push the limits of robust machine learning.
Wow. This deep dive has really been a whirlwind tour of robust machine learning. It feels like we've covered so much, from those sneaky adversarial attacks to the complexities of formal verification. I'm starting to see just how complex this whole area really is.
Yeah, it's definitely a lot to take in, but these insights are super valuable for anyone working with ML, especially in areas where reliability and security are critical.
Absolutely. So as we try to put all of this together, what are some of the key takeaways for our listeners who are already experts in this area? What should they be focusing on?
Well, I think the first thing is that just focusing on accuracy isn't enough anymore. We need to think about both security and reliability from the very start of the ML design process.
It's like when you're building a house. You don't just focus on how it looks. You have to make sure it has a strong foundation and can handle all kinds of stress.
Exactly. It's about taking a holistic approach, thinking about vulnerabilities and defenses at every level. The data, the algorithms, the hardware, and where the system will be used.
The research really shows just how many different ways ML systems can be attacked. It's like attackers have this huge playbook of strategies.
And they're always coming up with new techniques. To stay ahead of the game, we need to constantly be researching and developing new defenses.
Out of all the defenses we've discussed, I was particularly interested in formal verification. It's like having this mathematical proof that your ML system is doing what it's supposed to. That level of certainty seems almost impossible in such complex systems.
It's a really powerful tool, but applying it to those large, complex DNNs is a real challenge. Things like scalability, efficiency, and dealing with uncertainty in the real world are all areas that need more research.
And we can't forget about the reliability problems that just come from the inherent complexity of hardware and software. These seem less obvious, but equally important.
Totally. As ML systems become more and more common in things like self-driving cars and medical devices, reliability becomes essential. It's not just about stopping attacks, it's also about making sure the systems perform consistently, even when things go wrong.
The research talked about all kinds of techniques for dealing with hardware faults, things like error detection and correction codes, redundancy, even fault-aware training. It's like building multiple layers of protection.
Yeah, those techniques give us a lot of different options, but we need to think carefully about the trade-offs. Cost, performance, complexity. There isn't one perfect solution. The best approach depends on the specific application and how much risk you're willing to accept.
And then for those neural network anomalies, where the model has trouble generalizing from its training data, the key seems to be improving generalization.
You got it. Techniques like adversarial training and using synthetic data sets can help the model be more robust to variations in noise, so it can handle a wider range of real-world situations.
The research also mentions some open challenges and areas for future research in robust ML. What stood out to you? Where do you see the field going in the next few years?
Well, securing training data sets and protecting IP are super important for making sure ML systems are trustworthy and reliable. especially now that more and more training is being done on third-party cloud platforms.
So it's not just about securing the models themselves. It's also about protecting the data used to build them.
Exactly. We need better methods for encrypting data, techniques to stop people from reverse engineering models, and secure training protocols to prevent data leaks and manipulation.
The research also highlighted the need to formally verify the hardware used in these systems. It's a reminder that robustness isn't just about the algorithms. It goes all the way down to the foundation of the system.
Absolutely. We can't assume that the hardware is always going to be reliable and secure. Formal verification can play a huge role in finding and fixing vulnerabilities in the hardware itself.
And finally, there's the challenge of making sure that failures in one part of the system don't cause a domino effect. This sounds like a really complex problem that requires a systems-level view.
Yeah, it's about looking at the whole system, how the different components interact, and designing ways to isolate and contain faults. It's about building resilience not just in the individual parts, but in the system as a whole.
It's becoming more and more clear that building truly robust ML systems requires expertise in a lot of different areas. It's not just about understanding algorithms. It's about seeing the connections between hardware, software, data, and even the environment where the system is used.
You nailed it. And it's an area that's constantly changing, with new challenges and innovations emerging all the time. Staying on top of things requires us to keep learning, be open to new ideas, and work together.
Speaking of new ideas, the research briefly mentioned the idea of shifting our thinking from robustness to resilience. It's about moving beyond just preventing failures to actually learning from them.
Yeah, that's a really interesting concept. What do you think about that?
It suggests a more dynamic approach to ML. Instead of just trying to stop things from going wrong, we should also focus on building systems that can learn and adapt when they do.
I like that. Instead of just surviving challenges, maybe ML systems could actually use those challenges to get better and smarter.
It's like that saying, what doesn't kill you makes you stronger, but applied to machine learning.
Exactly. So instead of seeing failures as setbacks, we could start to see them as valuable learning experiences that make the system more resilient and adaptable. But how do we actually build that kind of resilience into ML systems? What would it take?
It would require a fundamental shift in how we design and train these systems. Instead of just focusing on accuracy with a fixed data set, we need to build in mechanisms for continuous learning and adaptation. The model would always be evolving, refining its understanding based on new information, new experiences, even its own mistakes.
So the system wouldn't be static, it would be a dynamic learner, constantly evolving and becoming more robust based on its interactions with the real world.
Exactly. But wouldn't there be risks in letting an ML system learn and adapt so freely? What if it learns the wrong things or starts to behave in harmful ways?
That's a valid concern. It really highlights the importance of responsible development. As we move towards more adaptive and autonomous ML systems, we have to prioritize building in safeguards, ethical guidelines, and strong oversight mechanisms. The goal is to make sure that the ML system's learning process is aligned with human values and ethical principles.
So it's not just about making ML systems more resilient. It's about making sure they are resilient in a way that benefits humanity and contributes to a positive future.
Exactly. As ML becomes more and more integrated into our lives, we need to prioritize not just its technical capabilities, but also its ethical implications. We need to make sure that ML is a force for good.
This deep dive has really been eye-opening. It's amazing to see the complexity and potential of robust ML. It feels like we've only scratched the surface. There's still so much to explore.
I agree. And to all of our listeners out there who are working in this field, I hope this has given you some new insights and ideas.
I think it's time to come up for air from this incredible deep dive. But before we do, I want to leave you with a final thought-provoking question. So as we move towards these smarter, more adaptive ML systems, how do we start thinking less about just building robust systems and more about cultivating responsible ML ecosystems? Robustness feels like just one part of a much bigger picture.
Yeah, that's a great point. It's not just about individual systems anymore. It's about the entire ecosystem they operate in, the data they use, how they're trained, where they're deployed, the regulations, even the impact on society.
Right, so it's also about the potential downsides of these increasingly powerful systems.
Mm.
We need to be careful about how we develop and use them to make sure they benefit everyone.
Exactly. And that responsibility goes beyond just the researchers and developers. It involves policymakers, regulators, people thinking about ethics, even the public. We need everyone to work together to make sure ML is developed and used in a way that aligns with our values and goals.
This whole deep dive has really shown how complex it is to build truly robust ML systems. It's obvious now that we need a deep understanding of the algorithms, the hardware, the security threats, and how to ensure both security and reliability.
Absolutely. But it's more than just understanding the technical stuff. We also need to consider the bigger picture, the ethical implications, and the potential impact on society. It's about looking at both the technical and ethical sides of robust ML.
Okay, so let's recap some of the key takeaways for our listeners who are already experts in this field. What are the most important things they should focus on as they continue to work in this area?
The first thing is to move beyond accuracy as the only measure of success. Robustness, which includes both security and reliability, needs to be a top priority from the very beginning.
So it's about building systems that are not only accurate, but also secure, reliable, and trustworthy.
Right. And to do that, we need to really understand the potential weaknesses and the different ways to defend against them. We talked about things like adversarial attacks, data poisoning, hardware trojans, side channel attacks. There's so much to consider, and it's constantly evolving.
The research made it clear that building robust ML isn't a one-time thing. It's an ongoing process. It requires being alert, learning all the time, and being ready to adapt to new threats as they pop up.
We also talked about all sorts of techniques for dealing with these vulnerabilities, things like gradient masking, adversarial training, pruning, encryption, and formal verification. There are lots of tools in the toolbox, but there's no magic solution. The best approach depends on what you're trying to do, how robust you need the system to be, and the trade-offs between security, performance, and cost.
And then there are those reliability challenges that come from hardware problems and the limitations of neural networks themselves. To deal with those, we need to really understand both hardware and software. We also need to use techniques like error detection and correction codes, redundancy, fault-aware training, and synthetic data sets to improve generalization.
We also spent some time discussing formal verification, which is this really exciting area where we can use math to actually prove that ML systems are doing what they're supposed to. It's still a fairly new area, but it has huge potential for ensuring safety in critical applications.
And we can't forget about the idea of moving from robustness to resilience. This suggests building systems that not only survive challenges, but actually learn and adapt from them, becoming stronger over time.
This idea of resilient ML systems that are constantly evolving and improving based on their experiences is really exciting. It could completely change how we think about training, designing algorithms, and even building the hardware these systems run on.
This deep dive has been a fantastic journey. It's been amazing to explore this world of robust machine learning. It's intellectually fascinating and incredibly relevant to how technology is changing.
I totally agree. And to our listeners out there who are pushing the boundaries of this field, keep diving deep, keep asking tough questions, and keep innovating.
Building truly robust, reliable, and respondable ML is a journey that requires everyone to work together, to never stop learning, and to be committed to creating a future where these technologies benefit everyone. So until next time, happy diving.